All right, let's see what you remember now. Chapter 15, we moved away from discrete. Chapter 13 was discrete, which is countable. Chapter 14 was an example of a discrete problem. So binomial, meaning it's repeated trials, and each probability is consistent, right? And there's only two scenarios. You either fail or you succeed. Now, you're in chapter 15, which is continuous. Now, in order to do continuous data, which I tried to explain last session about the rope, you have 10 centimeters. The problem is that there's no distinct total. There are infinite total in a length. The length you don't know where I can cut. The chances of me cutting a particular point is impossible to work out. So instead, we had to work through intervals. So there were two key factors in order for you to start solving any problems in chapter 15. It was called, PDF is the short way of writing it. But what does PDF mean? Rango. Very good. You know it is a chapter 15 or continuous random variable when you read the question and the first thing they say is probability density function. What does this mean? In order for it to be a probability density function, there are two key factors that you must know, and that's what examiners want you to demonstrate. What's one of them? Alex, do you remember? For it to be a probability density function, what must you have? It's okay not to be sure. No, Ryan.
The area underneath has to be one.
Okay, the area underneath a graph. Now, why is that? Probability density function, meaning because it's not discrete anymore, it's not singular data, it's infinite data. The problem is we can't work out and point the chances of a point. Now, just to bring you in, Alex, this is the logic. Imagine I had a rope that was 10 centimeters long, right? If I asked you, what's the chances of me cutting exactly that particular point? See, the problem here is that we don't know. What's the total? So if you said it's 1 out of, well, how many? Is it 1 out of 2, 1 out of 3, 1 out of 4, or 1 out of infinity? That's the problem with an instant. But if I changed the question, if I said, what if I took it as, I split it in half, so it's from 0 to 5, and then 5 to 10. If I asked you the same question now, but just changing one small thing, I said, what's the chances of me cutting anywhere between 5 and 10? 1 and 2. And the reason why you can do that is because I've now changed it to an interval. The interval splits it up into 2 sections. So you see 2 sections there. You can actually calculate the chances of that happening. But I could have made the interval smaller. I could have done it between, 7.6 and then 7.8. And you still be able to work out the chances because you can work out when it's interval. And because same thing with a function, so beforehand, when you were doing discrete, it was one data at a time, right? So you relied on the number of data that you see to see the distribution. The problem now is the data is infinite. You've got infinite possible data, so that's why it's continuous, right? The graph is continuous. So if we're going to use that interval, so in this graph, rather than dots, if I use the interval, so between 5 and 10 as an example before, this section under the graph has to represent the chances of it occurring. Because that's how you did it. You said 1, 2, so it's 2. That section has to be 1 out of the 2. So here, this now must represent the probability. But if this is going to represent probability, there are 2 things about probability that we know. One is what Ryan just said, the area under the curve has to add up to 1. Because the total probability can only be between 0 and 1. You're either 0% sure or you're 100% sure. So that means it's only between 0 and 1. That's why the area under the curve, so part 1, area under the curve, needs to equal to 1. But how do you find the area under a curve? Well, you learned that from integration. If this is f of x, that's the curve, then the antiderivative gives you the area. So negative infinity to infinity of a function needs to equal to 1. That's the definition in your mathematics textbook. All they're saying is, for it to be a probability, it means that if you add all the area together, it has to equal to 1. So that's one of them. What's another thing about probability they must have? So we know the probability has to be between 0 and 1. What else? Second point. It has to be bigger than 0. You can't have negative probability. It doesn't make sense to say negative 30% chance. You're either 0 or 1, right? It's between there. So it can't be negative. So if it can't be negative, the function can't be negative. Okay, those are the only two things that determines whether it is a probability density function. So as soon as they say you've got a PDF or probability density function, you are assuming two things. The area has to add up to 1, and the function itself has to be above the x-axis. Can't be negative. Okay? So because of this, all the questions that we're dealing is based on those first 2 points. That's 15A. Yeah. Yes. Well, yeah.
Can you have like we have a density median is between say 0, 1 and then 2 and 3. Can you have that, or does it have to be continuous across the whole?
That's a good question. It would then be a very specific scenario because the functions, for whatever reason, would disconnect between a certain interval. So in whatever the scenario is, if it does happen that way, I guess if you can model it that way, because the function can be anything, as long as it replicates the scenario, then that's okay. It'll be all right. It's just in general, when we say continuous random data, we're assuming that from this point, it's literally all accounted for. So there has to be some reason why it wouldn't account for that. But if there is a good reason for it, I see no problem with it not being, it can be discontinuous as well. All right, here we go. So what's 15B and C? It's just because I got 6 minutes now. 15B and C, we're now taking chapter 13 and putting it into chapter 15. Expected value and variance. I've already got the formulas there for you, but for you to remember, chapter 13, how do you find E of X again? Chapter 13. What was E of X equal to again? E of X is your mean. How do you find the mean again? Let's go with Samuel. Do you remember chapter 13? How do you find E of X again from chapter 13? Discrete random data. That's for chapter 14. That's not bad. So chapter 14, n times p is the expected value. What about chapter 13? Just one chapter back. What was that one? Yes, that one's for the variance. So we're going to do that one. So chapter 13. Sorry? Very good. Can I get, just for those who aren't listening yet, chapter 13, for you to remember the expected value, remember the probability distribution, it was actually just x variable times, thanks team, that was your probability. So remember, in your probability table, it's your x variable times the chances plus the x variable times the chances. Notice that formula is no different to continuous. So the continuous, how do you find the probability? It was the integration of the function between the intervals, the negative infinity to infinity. But then you times it by x because that's literally what we're doing. We're doing the expected value, but in continuous random variable. So what you learnt in chapter 13, the theory is still the same. It's x times your chances. But we literally just said from 15a just now, the chances of anything occurring, so probability of x equals little x is equal to the area under the curve. So if you wanted to find the expected value, isn't it just x times that? So hence x times the function becomes x dot f of x. Same idea. Yeah? And whatever you do for variance, which is the one that Ella said before, it's the same thing. This was e of x squared minus e of x all squared. That was your formula for the variance. Well, notice here, it's no different. That's still saying e of x squared. So e of x was x times the function. So the e of x squared must be x squared times the function. And then here, this is just your expected value, and you just got to square it inside here. That's it. Same thing. Okay, so did I put a square there? No, I didn't put a square there. Pretty sure there should be a square on this one here. I must have forgotten to put a square. on that one there. Okay, so this one is your expected value, and you got to square that. Okay, so that's your expected value, and you got to square that. Same idea. Okay, so whatever you do for chapter 13, you do the same for chapter 15. Cool. 2 minutes. I might have to do this next session. I wanted to do this problem because this ties in just what I just said. You find the median, you find the area, and you find K by using probability density function. So this is the type of question where as soon as you see this word, area must add up to 1. So the first part of the question, this is your function. Looks nasty? Don't worry, you got a CAS. Find the value of K. Here's your K. Can someone tell me what would you type on your CAS to find K? You know it's a probability density function. Pat.
Integral from 0 to pi on 2 of f of x equals 1, and then you solve for k.
Beautiful. This is what you would type on your CAS. Now, why is it 0 to pi on 2? Because they said the interval 0 to pi on 2 is where this function exists. That's the domain. But if it's a probability density function, then all those x values for that curve, the area underneath it has to add up to 1. So that's why Pat said it's the integral between 0 to pi on 2 for this curve, it needs to equal 1. Solve for it because we're trying to find k. Now, if you did that, the k should equal to 3. Okay, just because I did it before, k should equal to 3 if you did it on your CAS. But you can see all I'm doing there is using probability density function knowledge to solve this problem, which is a 1 marker. It's a CAS work. Okay, but that's 15B and introduction to 15C. Yeah, BBC. So variance, expected value. But we'll do that next session because it is now 9:40, and I want to give you a bit of time to look at your stacks as well. So today's lesson so far, intro to a bit chapter 15, looking at expected variance for continuous, and also looking at 14C again, knowing how to use your CAS to find n trials or number of successes. Okay, not easy, tricky ones.